All right, I'd like to welcome everyone to this Google Hangout. This seminar series is supported by a grant from the University of Central Arkansas Foundation, and financial support is appreciated by the Department of Physics and Astronomy at the University of Central Arkansas. Our seminar speaker this evening is Dr. Michael Busch. He has a BS in physics and astrophysics from the University of Minnesota and a PhD in planetary science from Caltech. He is currently a research scientist at the SETI Institute. We're very thankful to have him giving a seminar this afternoon on asteroid radar astronomy and space missions. Please take it away, Dr. Busch.
Okay. So I'll be talking about studies of near-Earth asteroids and various space missions connected to that, although my own work is primarily ground-based astronomy, so that'll be the bulk of the talk. One thing before I get started, if anything I say is really boring, please bear with me, and I hope it'll get more interesting. If anything I say is incomprehensible, please interrupt, and I'll try to clarify. Also, let me know if you can't see the pointer on my mouse when I'm doing the screen sharing, and I'll try to adjust things a little bit to explain a bit better. Learning myself how to start the video sharing here. Okay. So this is a plot of the inner solar system out to the orbit of Jupiter as of just about a week ago. The Earth is right about here, just approaching equinox. Mars is over on the far side of the sun just about now. Jupiter is over here. And then all of these small dots are different populations of small bodies. The red dots are near-Earth asteroids, which we'll be focusing on in this talk. You can see at any given time, there are some of them passing near the Earth. But most of the time, most of the objects are quite far away from us. Some get closer to the sun than Mercury, others get out as far from the sun as Jupiter, and even a little bit further. Now, on a time scale of a few million years, these near-Earth asteroids will be replaced. Their orbits aren't stable. They'll get scattered by gravitational interactions with Jupiter, they'll fall into the sun, they'll get broken apart, they'll run into a planet. That happens every so often. So where are these near-Earth objects coming from? They're coming from the main asteroid belt, which is, of course, between the orbits of Mars and Jupiter. There's several 100,000 main belt asteroids plotted here, as well as a few tens of thousands of Trojan asteroids that share the orbit of Jupiter a little bit further out, and then a significant number of comets that are just passing through. So when studying the near-Earth objects, we're actually studying the main asteroid belt, just the objects we're looking at being much closer to the Earth. Now, as obvious caveat, it may look like solid asteroids across the entire inner solar system, but this is about 1 billion miles of space here. So there's a lot of asteroids, but there's even more empty space. It's about as thinly spread as grains of dust, one on one side of the room, one on the other side of the room. There's lots of empty in between all the asteroids. It is made them large enough to see on this image. If we zoom way, way in, we can start talking about the asteroids as things other than just dots. And that's what this collage shows. So this is a collage of asteroids and comets that have been visited by spacecraft, excepting the two largest, Ceres and Vesta, because they are most of the mass of the asteroid belt and thus a little bit too big to be on the same scale as the others. Now, these three objects are objects in the near-Earth population that have been visited by spacecraft. And you notice they're considerably smaller. There's a reason for that. Something like Letitia, over on the left here, 130 kilometers across. That's going to be about 4.5 billion years old. It formed in the early solar system. Now, the reason we don't have a planet building up out of all of the objects in the main asteroid belt, which of course happened in the inner solar system, is because of Jupiter. It grew too large, too fast, and its gravity started scattering around the orbits of everything in the asteroid belt, to the point that when they were encountering each other, they were traveling far faster than their escape speeds. And they eventually started eroding each other rather than accumulating. Something like Letitia, well, it's eroded a fair fraction of its volume, is still going to be about 4.5 years old. 4.5 billion years old. Slight difference there. But the other objects here are a lot younger than that. These are the remnants of debris from previous asteroid-asteroid collisions. Something like Toutatis, 4.5 kilometers long, might only be a few million years, 100 million years old. And then in the last few million years, it's gotten kicked onto an Earth-crossing orbit. So most of the near-Earth objects that we see are this remnants of these collisional cascade in the main asteroid belt, and then getting transported onto Earth-crossing orbits. And if you zoom in even further, you can see that these are piles of rock and rubble. So reasons we want to study these things. Well, they are physically young objects. They're chemically still relics of the early solar system. So if we want to understand processes of planet formation, the environments in which the Earth, Mars, so on formed, it's useful to study the asteroids because they're another part of that process. And they chemically preserve a time period that really doesn't show up too much in rocks on Earth. Because, of course, early Earth was so large, all the gravitational radiogenic heat melted everything. And we don't have any 4.5 billion year old Earth rocks. But we do have 4.5 billion year old asteroids. So we want to study them. They're also very weird physical systems because we have these microgravity piles of aggregated rocks. And weird stuff happens to even fairly everyday materials in those conditions. We don't usually think of things like electrostatic forces, van der Waals bonding, being important for piles of rocks 100 meters on a side, small mountains, but it matters in the near-Earth population because the gravity of these objects themselves is so low. We also have to worry about things like radiation pressure, which is not usually a concern in terrestrial geology. And then some of the near-Earth asteroids are easy to get to for spacecraft. If you want to do missions in deep space, you can get to the near-Earth asteroids, in many cases, more easily than you can get to Mars. In some cases, more easily than you can get to the moon even. So that's a motivation to study them. The one that gets the largest amount of public interest, of course, is the asteroid impact hazard. I mentioned that occasionally asteroids hit planets. Sometimes that planet is the Earth. Many of you have probably seen videos, YouTube, and so on, from Chelyabinsk in Russia. Southern Ural Mountains, just over 3 years ago now. An object 15 or so meters across, so based on what I can see on the video, the size of the room you're sitting in, came in a fairly shallow angle above town, and of course, it's coming in several kilometers per second above escape speed, and it has a huge amount of kinetic energy. And as it comes deeper and deeper into the atmospheric density goes up exponentially. It eventually reaches a point where it's intercepted it's equal to its own mass in air, and it deposits almost all of its kinetic energy into heat and light and sound. It's equivalent to setting off quite a large amount of tons of TNT, 11 or so kilometers in the air. Nobody died, but it was a very near thing. There were about 1,500 people injured and about $30 million in damage. Primary cause of injury was actually from glass. What do you do if you see a bright light in the sky?
You look.
If you're smart, you duck under your desk, which a lot of people do. School had just started early morning when this happened. But if you're curious, you run to the window, and then 30 seconds later, the shock wave, which is traveling at the speed of sound, hits the window and blows all the glass into your face. Or you're sitting in a room and you're not wearing shoes or whatnot, and now your floor is covered in broken bits of glass because the window just got blown in. So that was most of the injuries. A few things were more serious, people throwing down flights of stairs and so on. Something like the Chelyabinsk event happens somewhere in the world every 30, 40 years. The last time that one happened that we have good records of was over the South Atlantic Ocean in the late 1960s. Really It was not noticed by anybody or anything except for the earliest comprehensive nuclear test ban treaty monitoring satellites, which noticed a very large bright flash in the atmosphere, but no corresponding pulse of gamma rays or high energy particles that you'd have if somebody set off a bomb. Instead, it's just a pile of rocks flashing in the air above the South Atlantic Ocean. Nobody lives there, so there wasn't any particular problem. There's similar or more scattered reports of an impact over the Brazilian Amazon in the 1930s, and then a larger event than even the Chelyabinsk one in a place called Tunguska, much further east in Siberia in 1908. And again, nobody's reported to have died, but it flattened an area of trees over a section land about the size of downtown San Francisco, near where I am here in Mountain View. Obviously, we prefer to know about things like this if they're going to happen over a city in advance. And while they're far less common, we prefer to know about impacts due to larger objects, say 100 meters across or larger, with decades or centuries of notice that we can do stuff about. So that's really been one of the larger motivations beyond just the scientific interest for surveying the near-Earth population over the last 15 to 20 years. And interest has gone up significantly in the past few years because of Chelyabinsk, although a lot of the programs I'll be talking about were begun before that. So currently the main method for discovering near-Earth asteroids is wide-field ground-based survey programs. The two most active right now are the Catalina Sky Survey, which is in Arizona, and the Pan-STARRS project, which is on Haleakala in Maui, Hawaii. There's also a little bit of work that is done from space using the Wide-Field Infrared Space Explorer. This is a NASA satellite that was initially intended almost entirely for astrophysics, mapping out star-forming regions, looking at survey brown dwarf stars, for many other things. But it became clear that a space-based survey telescope working at wavelengths around 10 microns is really, really good for surveying and studying near-Earth asteroids, because near-Earth asteroids that are at 1 AU from the sun are at about 250 Kelvin, give or take, depending on their albedo. Can be a little bit hotter, can be a little bit colder, and therefore are emitting most of the peak of their thermal emission around 10 to 12 microns. It means law calculation, that's where the peak is. So the brightest possible wavelengths. And this is convenient because the Y spacecraft is designed such that it has solar panels and a heat shield here between the spacecraft and the sun. That keeps the spacecraft cold, and it just scans at 90 degrees away from the sun on the sky as it orbits the Earth. If we're on the ground, and we're observing 90 degrees from the sun on the sky, we have to be observing fairly close to twilight. And that means we have a lot of sky brightness from scattered light from the sun being bent around by the atmosphere. So WISE can find some asteroids that we have a very hard time discovering from the ground. There's another project now called NEOCAM, which NASA is investigating as a new dedicated asteroid finding mission, which uses the technology derived from WISE to survey much closer to the sun, down to 60 degrees, for instance, where ground-based programs can't go at all. And there's been some demonstrations, a small satellite mission from the Canadian Space Agency doing a similar thing. So it may be that in the future, a lot of asteroids are discovered from space, but so far, most of the discovery has been from the ground. And right now, we're discovering about 1,600 near-Earth asteroids every year. The goal here is to discover, again, almost everything bigger than 100 meters across. If you do the calculation for if there's an asteroid that's going to hit somewhere in the world at random, when is it definitely going to be worth deflecting it? It's around that 100-meter size or larger. We can say right now that nothing bigger than 1 kilometer in diameter will hit the Earth in the next couple hundred years. The surveys are complete to that point. But we have to do a lot more work to push it down that another factor of 100 in brightness, because we're going down 10 times in diameter. The current survey programs won't quite get there if they're just continued indefinitely. The Large Synoptic Survey Telescope, which is currently just beginning construction, designed to survey the entire night sky repeatedly every night, would get to that discovery goal of 100 meters across. But it would take a long time because objects on orbits that are very similar to that of the Earth, you can just envision with the Earth's orbit around the sun, if you project it onto the sky. I'm going to switch off the screen sharing for a second so that I can wave my hands around. So we have, if I'm sitting on the Earth and I'm looking at the sun, the Earth's orbit goes like this. Never more than 90 degrees away from the sun, and almost all of it is much closer than that. So I have an object on a very Earth-like orbit that's potentially hazardous, but it spends most of its time near the sun on the sky. And I'll give a couple of examples of individual objects with orbits like that later on. So a goal for something like NEO-WISE and the NEOCAM project, surveying from space, is to catch those objects much closer to the sun than we can see them on the ground. They eventually do loop out far enough that we can find them from the ground, but that would take 20 years. So if you do it with something like the NEOCAM project, you can shave a certain number of years off the estimate. So the question for NASA and the other space agencies and the US government and the other governments that fund the other space agencies is, how much do you want to invest in finishing up the survey by a given time? So given that we have discovered all of these asteroids, what do we do next? So we have a problem. We can't really resolve most of the near-Earth asteroids. I showed you spacecraft pictures. It's very expensive to send a spacecraft out to an asteroid. Although there are reasons to do that for individual objects, which I'll talk about. But we want to survey the entire asteroid population and get very good constraints on their orbits. We need some way to get very high precision and preferably resolved images of the objects. Far better than we can get with normal astronomical survey images, which are limited by atmospheric seeing, because the atmosphere is around the ground, or just the size of the telescope that we can afford to lift into orbit. Or even better than what you can get with adaptive optics techniques. So one technique we use to do that is techniques of radar astronomy. And we have 3 primary telescopes we use for this, although we are using others now. The Arecibo Observatory in Puerto Rico, which is still the single most sensitive radio telescope in the world, although the 500-meter aperture spherical telescope, which looks like Arecibo, except it's significantly larger, although it won't be that much more sensitive, is currently being constructed in GHO in southern China. So when it comes online, it'll be able to do many of the things Arecibo can do. But what it won't be able to do, that Arecibo can, is that up here, at the focus of this 300-meter wide spherical reflector, we have mounted a very, very high power radar transmitter. It puts out about 800 to 900 kilowatts of power in a very narrowly focused beam. Beam goes out into space, bounces off of the radar target, and then the radar echo comes back down and gets received. Now Arecibo is very sensitive, but because it's 300 meters wide, we can't tilt it sideways. So we can only look within about 20 degrees of straight up just by moving around the secondary and the tertiary reflectors up here on the platform. So the 70-meter Deep Space Network antenna in Southern California, DSS-14, which is one of many telescopes that NASA uses to communicate with spacecraft beyond Earth orbit, can look over much more of the sky. And we've mounted a transmitter there, down now here at the base of the telescope, because the optics are a bit different. That puts out about 450 kilowatts. Now, Goldstone is much smaller than Arecibo, so it's a lot less sensitive for radar receive, just because it collects fewer photons. But it can see more of the sky, so there's complementary capabilities there. More recently, we even got an even less powerful transmitter installed on a 34-meter antenna, DSS-13, which is also in Southern California. I mentioned that one because there's a scheduling crunch with the 70-meter Deep Space Network antennas. Priority, of course, goes to deep space spacecraft communications. If you wish to downlink data from Cassini at Saturn, you need a 70-meter antenna. If you want to downlink data from the New Horizons spacecraft, you need a 70-meter antenna. So last year, when New Horizons was flying by Pluto, there were actually a bunch of asteroids we wanted to observe with radar techniques at the time. We couldn't get time on the 70-meter whenever Pluto was above the horizon. But there's some spare capacity with the smaller antennas that don't get oversubscribed quite as much. So we've been using that smaller facility as well. So we send out a radar signal. What does this tell us? We code the transmitted signal in time and in frequency. And that lets us resolve the target object. So you see there on the left a series of images. On the right, there's a schematic of what's going on. And again, I'm going to switch off the screen sharing. This may get a little bit confusing because I'm used to doing this where you can see both me and the screen at the same time. We have an object out in space, some complicated shape. It's spinning. We track the object's center of mass as best we know. Prediction of its orbit. We need to have that in order to point the telescope at it in the first place. The radar beam is a narrow section of the sky, so the odds if we aim at a random section of the sky that will hit something is actually really, really low. We track the object's center of mass, so we know the frequency we expect that echo to come back in. The object spinning, part that's rotating towards you gets Doppler shifted positive, slightly blue shifted. Part that's rotating away gets Doppler shifted to the red, a little bit negative. So we're getting slices now across the object in a dimension parallel to its spin axis. So that's one dimension of resolution. We get a second dimension of resolution by slicing the object in time delay. So we can't time how long the radar signal takes to come back, and we slice it along this direction. This gets a little bit complicated to interpret because in any individual image, I can't tell you if a feature is in the northern hemisphere of an object or in the southern hemisphere of the object because those are at the same delay Doppler position. Now, if you've got a bunch of images from different angles, we can figure out what's going on, even with some very complicated shape. So you see there in the left-hand side of this slide, an object called 2000 RS11. We give these asteroids telephone numbers rather than names because we know 13,000 near-Earth asteroids now, and it would be really annoying to have to come up with 13,000 names. But you can see immediately this object is what we call a contact binary. We've got two pieces sitting on each other. A larger piece here, a smaller piece a bit further back, and of course, as the object rotates, which one is in front and which one's behind swaps back and forth. And in this case, we have enough data that Kaylee Brower, who was a summer student working with me last year, was able to say that 2000 RS11, turn off the screen sharing again, looks like this. Sorry, 3D prints are fun, but a little bit cumbersome if I drop them. So we've got two pieces sitting on each other. The whole thing is 800 meters across, and it's flying around the solar system. Because we have resolved images, we're able to tell where it is in space to significantly better than its size. So a couple hundred meters precision. And that's a lot better than you can do with optical imaging, which might be uncertain by tens or even hundreds of kilometers, depending on how good your resolution is and how far away the object is from the Earth. And that lets us run on RS11's orbit several hundred years in the future and say that it will never hit the Earth. And we can do that similarly for several hundred other asteroids. Now there's some limitations here because the radar signal strength drops off as the 1/4 power of distance from the Earth. So our impact predictions are limited to objects that we can detect, obviously. We can detect a golf ball at the distance to the moon, but further away you go, the radar signal spreads out as 1/r² going out and 1/r² coming back. So a few lunar distances away, we can detect something only a few meters across. By the time we get out to the main asteroid belt, something would need to be 40 kilometers wide for us to see it. So these high precision orbit predictions really only work for near-Earth objects. But those are the ones that have the impact hazard, so radar is well suited to characterizing their orbits. I've also have a note on the slide here about something called the Yarkovsky acceleration. This is a little bit of a tricky thing. We have an object out in space. It has some shape. It has some cross-sectional area. There's radiation pressure because sunlight hits it and gets reflected off. So there's direct outward force from the incoming sunlight. There's also an acceleration from the heat off the object. The afternoon side will be a bit warmer than the morning side, so it's asymmetric, and you get a net acceleration. This was first worked out on a theoretical basis by Ivan Osterovich-Yarkovsky a bit over 100 years ago now. The application to spacecraft became clear, of course, when people started launching small spacecraft with very low mass per unit surface area. Application to asteroids, we got realized more recently. But it turns out to matter for these long-term trajectory predictions. Sunlight is pushing these mountains around. So there you really need to know the shape and the size to constrain that nicely. And if you can measure the acceleration with, for instance, repeated radar pings, we can get the object's mass and density, which is really hard to get for single asteroids without sending a spacecraft out there. It's obviously very important if you're talking about deflection of an object that might hit the Earth, because how massive it is determines how much momentum you need to apply to move it. It also matters for discussions of asteroid formation, how much empty space there is inside this pile of rubble. Now, I'm going to gloss over this a little bit just to save time, but one benefit we've had lately of increased resolution. So for objects that are close enough to do this, our resolution is limited by how fast we can code the outgoing radar signal. Used to be we could code it only to about 8 megahertz, modulating that signal 8 million times a second, which if you work out the math gives you a resolution in range of a bit more than 19 meters. Now for some objects we can push down to 40-meter modulation, which gives us 4-meter resolution on various objects. And that's the difference between being able to say, okay, it's a contact binary a few hundred meters long, see on the left, versus, oh, there's a bunch of boulders and blocks piled on the surface over on the far side of this thing, and some complicated structure at the joint. And then we're starting to get down to the point where we may be able to do 2-meter resolution on a few objects. So we really can start doing more detailed geology for objects that pass close enough to the Earth. I mentioned we do use other telescopes besides the 3 that have transmitters. One reason we might do this is to transmit from one telescope, bounce the radar signal off, and receive with a second telescope. This is called bistatic radar imaging. This is important for objects that are passing very close to the Earth, because it takes us a finite amount of time, a few seconds, to physically move the transmitter out of the path of the telescope optics and put the receiver in the path so that we can record the radar echo. And you can imagine if the object is 3 light seconds away and it takes us 3.5 seconds to switch over, by the time we switch to receive, all of the radar echo that we sent out has gone out to the object, come back, flown past the telescope. So in that case, we do need 2 telescopes to actually see anything and to get good Doppler resolution. So lately we've been doing a lot of stuff, transmitting with Goldstone, receiving with the Green Bank telescope in West Virginia, in part because the GBT, it's easier to get time there than on some other facilities. And it's a bit larger telescope, 100 meters wide, the largest telescope in the world that's steerable, so you can look at things that Arecibo can't. All right. So I'm going to give a test case for you. This is an object called 2015 HM10. So the telephone number just means that it was discovered in 2015. In this case, it's actually discovered in the southern hemisphere by the Dark Energy Camera, which is at Sierra Tololo in Chile. The DECCAM is designed, of course, for cosmology, searching for effects of dark energy by charting very great detail the expansion of the universe. But occasionally asteroids fly through in front of all the galaxies they're studying, and they log them and report them. So HM10 was discovered that way. And it came just over 1 lunar distance away in July of 2015. We quickly learned from Bill Ryan, doing optical observations from Magdalena Ridge in New Mexico, that it's spinning every 22 minutes. Now, that rapid rotation tells us a couple of things. One is that the object is having to hold itself together by cohesion. Because for an object that's held together only by gravity, it can only accommodate a certain amount of rotation before centripetal force causes it to fly apart. For an object with typical asteroid density that critical spin period is about 2 hours. Here it's spinning 6 times that. It has to have some cohesion. We also can tell based off the absolute magnitude of the thing and the magnitude of the light curve that it was fairly small and very elongated. Fortunately, we were able to get lots of high-res radar imaging using Goldstone and Green Bank, as well as all the other facilities that we could get time on. So just to show you what the result is for this object, you can see here the series of images. They span about 30 minutes, which is just over 1 rotation period. There's a bit of a gap on the top left between the first image and the second, because we were switching setups around, so there's just a few minutes where we were taking data. You can see that the object is indeed very elongated. We're seeing it broadside and then end on, and then broadside again. So it's 80 to 100 meters one way and 40 to 50 the other way around its equator. We don't really constrain the pole-to-pole dimensions that well because we were looking roughly near the object's equator. So I can't really tell you how much it's extending effectively out of the plane of the screen. But you can see it's very elongated. And unlike Kawa, which was, or some of the other objects I showed you that are covered in boulders or blocks, this one doesn't have that many. It's got some facets. You get a flat area here that's only the resolution here is 4 meters, so that really is a flat facet, 30, 40 meters across, and then really quite smooth. But so it's not the same rubble pile structure that you have for larger objects. The cohesion means that it's arranged somewhat differently. But there is something back here that's relatively high standing, which may be a boulder or block sitting on the surface. So this starts telling us things about the internal structure of these piles of rubble. They're pretty weak, 25, maybe 100, 150 pascals, depending on the density is required to hold it together. Now, that strength may seem low for any material stress limits that you're familiar with, and it is. But roughly what you get if you have a pile of flour that's slightly sticky, or a pile of coarse gravel. Again, we don't usually think of cohesion mattering for piles of sand 100 meters across. But in this very low gravity environment, it is significant. Now these cohesion numbers also matter, of course, for the impact hazard, because how an object reacts to getting hit by a hammer, for instance, depends on its material properties. It also matters for things like asteroid sample return missions. You want to go up there and grab a piece off the surface. The fact that it's spinning so quickly and you actually have to physically press into the surface to stay put, and then exert quite a lot of force to pull up a block, that matters to mission design. All right, more typical case study for us, the asteroid Toutatis, which we saw a photo of briefly before. Toutatis has been observed for a really long time. It was discovered initially at the beginning of 1988. It's close to, but not quite, in a 4-to-1 orbital resonance with the Earth. So it goes around the sun a bit less often than once every 4 years. So we observed it with radar imaging in 92, 96. I say we, I did not do this. Steve Ostro, who was my thesis advisor, started the project, and then I took over many years later. Based on that, Steve and Scott Hudson, who's at Washington State University, managed to develop the shape model and understand Toutatis' complicated spin state. It's tumbling around in a pretty complicated way. And became clear later on that, from observations I did in 2008, that Toutatis is getting spun up and down by effects of flying by the Earth. So it's elongated and bifurcated, this contact binary shape. And as it flies by the Earth, it gets torqued up and down by the effect of gravitational tides. So the Earth's gravity pulls a bit more on this end than on that end, and then in effect is to try to angle it towards the Earth. Now if it was spinning very quickly, that would average out. It would get spun up a little bit and then spun down a little bit. If it was spinning very, very slowly, it would get spun up slightly and then spun down slightly, and it wouldn't matter. But it happens the spin period is effectively a few days, and during the closest approach in 04, it was pretty much ideally arranged. and it lost a part in 1,000 of its angular momentum just due to gravitational tides from the Earth in that single flyby, which is the closest to the set. And then it's also getting torqued up and down to a lesser degree by the Sun and the Moon and Jupiter. And we can see those effects in the dynamics from the radar imaging. It's because we have this really high-resolution data set over this entire time span. Now, it's still weird for me to think about. This asteroid is out in space 100 million kilometers from anything, and it's getting spun up and down by effects of gravitational tides in a way that we can see. It happens to the Earth, but in a measurable sense, but that's... We measure the rotation of the Earth far better than we measure the rotation of Toutatis. But again, this thing's small and elongated, so it can get affected by stuff you don't normally worry about. The other thing about Toutatis, which is that it keeps coming back, because it's in this 4-to-1 resonance. So it got observed in 2008, and then in 2012. 2012 was the last close flyby of this set. And we were planning an extensive campaign of radar imaging. And then I learned something interesting. The Chinese Space Agency lunar program, the Chang'e series, had the Chang'e 2 spacecraft, which was mapping parts of the moon. So they could land the Chang'e 3 spacecraft and the U-2 lunar rover. After they'd done that, they had a little extra fuel on board. And they did a complicated series of dynamics to send Chang'e 2 just past escape speed out of Earth-Moon space entirely, so that it would fly by Toutatis when Toutatis was coming near the Earth. So at the same time as I was getting the radar pictures on the left, the Chang'e 2 spacecraft was flying by Toutatis and getting the sequence of radar images, the sequence of optical images on the right. Now, it was never designed to do this. They got only 30 seconds of data. Designed to image the moon. When you're orbiting the moon, you're traveling at 1 kilometer a second, or 2 kilometers a second, depending. In orbit, you're not in orbit around Toutatis, instead you're flying by at 11 kilometers per second. So they just got one brief set of snapshots as actually the asteroid was flying away from the spacecraft. This is after closest approach. And you can see the shape model that we derived and the radar images are showing us the same features that are actually there on the surface. So here's the big end, the joint between the two components, the little end, and these boulders or blocks here on the little end of Toutatis are the same features we're seeing in the radar images here and here. So stuff that I'm showing you when I'm showing you these radar pictures is in fact real. Now there's a few limitations. I hadn't seen the big end straight on like this before. So the old model I have the 3D print of isn't correct. I have to go back and fix it. The other thing is that the radar imaging gave Toutatis's position accurate to within a few hundred meters. It also gave the orientation accurate to within about 10 and 15 degrees, which meant the Chang'e 2 team could fly the spacecraft very, very close to the asteroid. They ended up passing about, on the scale of this picture, 1 or 2 lines below the A that I've marked in the image. They were only 880 meters, give or take, above the surface of Toutatis. That actually was significantly closer than they had planned. They had planned to be 1.5 kilometers or so away, just to be entirely outside the uncertainty space, but they were able to get that close at all because we knew very well where Toutatis was going to be. So that was cool to see happen.
So Michael, did no one know that they were planning to do that, or did they just realize that they had enough fuel and so go for it?
So we had made all of our Toutatis observations through 2008 public. And then the spin state model, we presented it at conferences in 2012. So it was already pretty much in the public domain. The paper didn't come out until 2013. But that information was out there in public. The Chang'e 2 team then decided, I think in part because China, of course, wants to demonstrate new technology, deep space communication and navigation is one of those. And they had not yet done a Mars mission because the Mars mission they had launched had been a ride along with the Focus Grunt Russian mission, which ended up splashing down in the Pacific.
Right.
So they want to demonstrate deep space navigation. They have a spacecraft at the moon that has enough fuel to do this. And they parked it around the Earth-Moon L2 Lagrange point on the far side of the moon. in what we call a halo orbit. They had it there for 6 months, waiting just the right moment to give it the burn to fly it out to Toutatis.
Nice.
I only knew they were planning this when I heard, oh, they've moved the orbit of Chang'e 2. Because people looking at the moon, of course, see the Chang'e 2 spacecraft in orbit, and the LRO spacecraft, and everything else. And then suddenly it's going somewhere else. And then I established some communication with Huang Zhengcheng, who's the chief engineer of Chang'e 2, with Zhizhonghui, who's a scientist at Purple Mountain Observatory in Nanjing, and we arranged that data that they got, they made it public eventually, and the data we got, we made public. So there's restrictions that were imposed by Representative Frank Wolf in the U.S. Congress, who is now out of office. But the restrictions remain that prevent NASA and NASA-funded researchers like me and the government-funded researchers like the Chang'e 2 team from collaborating with each other in certain ways. But making things public jointly managed to work.
Cool.
And now they are planning a dedicated Chinese asteroid mission.
Cool.
We'll go to some other objects.
That is very cool.
So we'll see what happens in the future. All right, another case study for another mission target. This is the asteroid Bennu. So Bennu is about 500 meters across. It's spheroid. So it's bulged out around the equator a bit, but it's basically a spherical pile of rocks. It's what we call a carbonaceous chondrite. Meteorite analogs for this are some of the oldest solid material in the solar system. They formed pretty cold environments 4.5 billion years ago. So Bennu is, again, a relatively pristine sample of that reservoir, which motivates going out there and grabbing samples of it and bringing them back to the Earth. Now, Bennu in particular is selected for this because there's radar observations from 1999, 2005, 2011. You see here the images from Arecibo from 2005. This is work led by Mike Nolan, who's now at the University of Arizona, working with the Osiris-Rex spacecraft mission team. And the idea there is to fly out to Bennu, which has the phone number 1999 RQ36. And you see its orbit is not too dissimilar from that of Earth. Mars is out here, which is why we can only observe it from the ground every 5-6 years. That's when the orbit syncs up. The next time that it's passing near Earth is when you can send a spacecraft up there and get samples. Now, Bennu is also interesting in that it does make these repeated close flybys to the Earth. And as of the last assessment, there is 3.7 chances in 10,000 that the asteroid will hit the Earth somewhere between 2175 and 2200. Bennu's orbit is slowly precessing, and for those 25 years, its orbit intersects the Earth's orbit closely enough that the Earth could intersect where Bennu is. Now, it's hard to predict asteroid orbits accurately out 200 years in the future, even with all this high-resolution radar data, because those close flybys keep amplifying the uncertainties. So motivation sending spacecraft out there, in addition to the science, is rule out those potential impacts. So NASA has a plan to do this called Osiris-Rex. Now, Osiris-Rex is initially motivated by asteroid sample return, wanting to go to a primitive asteroid, picking up samples in context, bringing them back to the Earth. Meteorites that we have on the Earth are all to some extent contaminated because they hit the Earth, they pass through the atmosphere, they hit the ground. Even if you pick them up immediately, they get exposed to water, they get exposed to mud. Well, not so much mud, because they land in Antarctica, but then even more water because it's all ice. And so you got some degree of contamination of your sample. This way we can go up to the primitive object, pick up the rocks, put them in a sample container, bring them back pristine and intact. So that was the science motivation. Bennu was selected because it synced up with the timeline and because we want to rule out this chance of Earth impact. So Osiris-Rex will launch in under 6 months now. September of this year, fly out to, or it may be slightly under 6 months, maybe just over 6 months, depending on when the launch window they do in fact go up. But they'll arrive at Bennu late 2018, pick up samples off the surface. And again, that mission planning was really helped by the radar imaging, because we can say Bennu looks like this, and if its density is not too far from uniform, we can say which areas of the surface have high slope and which areas are flat. So you expect the fine-grained material to settle in the flat spots. We see this on other asteroids that we've looked at with spacecraft. So it ends up that this should be fine-grained material, which you can pick up and put in the sample container, or the robot can do that, I should say, right around the asteroid's equator. So that tells you where you want to land. You don't want to land up here because that's this block, which is 15, 20, maybe 30 meters across, and it's got really steep slopes all around the sides of it. And you don't want to try to land on the side of a hill. That's really awkward because you're basically steering an inverted pendulum.
Yeah.
With the spacecraft mass up here, and it's getting pulled downwards very weakly by the asteroid's gravity. But that's not a stable configuration. It wants to fall over. So you have to do, it has to autonomously do a complicated accurate control algorithm when it's doing this touch and go and grabbing samples. So it's good that you have flat spots to do that. So that's the current asteroid mission set from NASA's side, but there are lots of other asteroid missions happening because, as I said, the asteroids are easy to get to. So there's 3 near-Earth asteroid missions that have already completed. I mentioned Chang'e 2, which is the most recent. There's also the Hayabusa mission, which is a Japanese space agency project, JAXA. Launched in 2003, flew up to the asteroid Itokawa, which you see here, I showed you earlier. Landed in the flat spots right around here at the neck between the 2 components. Picked up a small amount of fine-grained dust, which is now sitting in labs in Japan, getting analyzed atom by atom. Prior to that, there was the NEAR Shoemaker spacecraft from NASA, which landed on the asteroid Eros, which is the 2nd largest near-Earth asteroid. So that was the first asteroid mission of any description, which launched almost 20 years ago now. Wow. And then Hayabusa and Chang'e 2 more recently. Hayabusa 2 is JAXA and then the European Space Agency, with a little bit of contribution from NASA. Went to the asteroid Ryugu, or en route to the asteroid Ryugu. Now, there's some technology improvements here in comparison to Hayabusa 1. It has a little lander package provided by ESA, which will ideally hop around the surface actually using a complicated spring arrangement to waft itself around. It's kind of outrageous, but it should work. The engineers are right. And that'll let you get up-close contact surface analysis of a lot of the asteroid. And then Hayabusa 2 is also designed to take samples from part of Ryugu's surface, and it also carries what is effectively a shaped charge grenade. The idea is to take a copper ball with an explosive charge around one side, release it from the spacecraft on a timer. The spacecraft hides a good long distance away with the asteroid in between them. The explosion goes off and makes a crater a couple of meters deep. And that way we get fresh asteroid subsurface. We can compare, for instance, the effects of radiation, high-energy particles bombarding the surface versus the effects at depth. And that's relevant, again, to understanding asteroid evolution, also relevant to things like planetary protection. If you're talking about objects that come from Mars, which some asteroids do, and there's organic material in there, how does it get preserved over the span of getting travel across the inner solar system? And how much organic material from the early solar system gets preserved? So how pristine do we need to make our spacecraft when we're trying to get samples of carbon compounds from Mars or from asteroids? So there's applications there. In addition, the effects of impacts onto asteroids are kind of relevant to asteroid deflection. So Bennu I've talked about, which has some contributions from the Canadian Space Agency as well as NASA. NASA is also dealing with a project now called the Asteroid Redirect Mission, called ARM. This would go to an asteroid called 2008 EV5, pick up a very large sample, 20 to 50 tons, versus a fraction of a gram for Hayabusa 1, and then between tens of grams and a kilogram for Hayabusa 2 or Osiris-Rex. ARM would not bring this huge mass back to the Earth. Instead, it would park it in a distant orbit around the Earth and Moon. And there's reasons for that I'll talk about. ARM would also demonstrate a technique for deflecting near-Earth asteroids. So in the 10% or so sort of chance that we do find a large object that we do need to move off an Earth impact course, we want to be able to test the technology to do that. There's a couple of ways that people have talked about. One of them is something called the gravity tractor. An ARM asteroid redirect mission would do that and demonstrate it on the asteroid 2008 EV5, which cannot hit the Earth anytime in the next several hundred years. So it's a safe place for ARM to test the technology. There's also a project called AIDA, which would be joint between NASA and ESA. That would demonstrate kinetic impact or asteroid deflection. So taking a much larger spacecraft than the Hayabusa 2 detonation test, running it into the asteroid at a very, very high speed, measuring the deflection to its orbit with a second spacecraft that would be provided by ESA. And that would actually go to a binary asteroid called Didymos. So you'd see an asteroid and you see its satellite, and you run the impactor into the satellite to see what happens. There's some science you can do there, asteroid internal structure and so on, in addition to the impact defense, the planetary protection impact hazard mitigation angle. So we'll see what happens if NASA and ESA elect to pursue AIDA or not. An EA Scout is an asteroid, small satellite technology demonstration mission NASA's going forward with. I mentioned there's discussion by other space agencies, China doing some stuff. There's some additional proposals to NASA, ESA, JAXA. I've heard some rumors of interest in asteroid missions from ESRO, the Indian Space Research Organization. So we'll see what happens. Again, the near-Earth asteroids are popular places to send out spacecraft to because they're such easy spaces to get to. And we know a lot about a lot of them. So I'm just going to finish up by talking about 2008 EV5, which is now the target of the ARM mission. I have a special interest in this one because studying it was a large part of my PhD thesis. So I'm a little bit biased. So EV5 is on an orbit that's very similar to that of Earth. It differs from our orbital period by about 1/15 of a year. So right now it's on the far side of the sun. But in 2008, it was passing near the Earth, and that's when it was discovered. And then in mid-2020s, it passes by the Earth again, and thus it's easy to get to for spacecraft in that time period. So if you look at the radar images, you'll see little features like this, that little bright pixel I've marked. You see that high standing relative to the surface around it because this is a delayed Doppler radar image. Distance from Earth goes from top to bottom. This is the terminator. Anything that peaks up above it has to be high standing relative to the surrounding surface. So there's a boulder or block sitting there near EV5's south pole. And there's some others scattered across the surface. Now, the ones that I can see on EV5 are maybe 15 meters across. Boulders or blocks that are the size the ARM spacecraft will want to bring back are going to be a lot smaller than that, a few meters across. But given that there are large blocks, and from the radar scattering property of the surface, there's small cobbles 10 centimeters across, there should be lots of things for ARM to choose from in that few meter size range that they want. EV5 has a shape very similar to that of Bennu, except there's a dent here, breaking the equator-aligned ridge. This shape is pretty common among near-Earth asteroids. It's what you get if you have a roughly spheroidal shape that gets spun up under influence of radiation pressure torques. It's actually analogous to the Yarkovsky effect. And it bulges out around the center to accommodate the extra angular momentum. But then, what is this dent? Is that an impact crater that came in and excavated material? Is it just the arrangement of blocks? We don't really have the resolution to say. This crater incident, dent or cavity, or this gap, is this feature over here on the right-hand side in this picture. There's a smaller structure here, which is also reproduced in the shape model. So the carbonaceous chondrite, which again makes it interesting from asteroid science standpoint, is another reservoir of material from the early solar system. Bit of a different mixture than we'd see in Bennu or Ryugu. So there's motivation to sample lots of different objects because we're getting different parts of the pre-solar nebula. And then there's boulders or blocks that you can pick up. So we think if you were to stand next to EV5, it would look kind of like this. It's just the Orgueil meteorite from France. Again, it's kind of contaminated. There actually was a notorious hoax with this one. a seed got stuck into it when either deliberately or when it landed in a field in France by accident. Somebody looked at it and said, "Seeds from space." No, that's not what happened. But the overall composition, less the terrestrial contamination of EV5, probably looks something like this. But the exact details of that are what we want to know. So the asteroid redirect mission, there's a detailed report now, which actually just got released today, giving the final mission plan. They've launched a robotic spacecraft to EV5 in 2019, 2020. And they collect this 30-ton boulder block, which would be 3-4 meters wide. The armed spacecraft itself would mass maybe 10 tons. So you've got very large solar panels. You've got a fuel tank in here, which would be a bunch of xenon. And then you've got a huge array back here of solar electric propulsion thrusters. So ion engines, Hall effect thrusters, any of a number of approaches that rely on ionizing the xenon gas and shooting it out of the spacecraft at very, very high speed by running it through a large potential drop, just high electrical voltage. This is very convenient in that it gives very large amount of momentum transfer per unit fuel. You can't use this to launch from the Earth because the thrust is very low, but it's very, very good for efficiently moving large masses of material around. No solar electric propulsion on quite this scale has been attempted before. The largest flight units are maybe 1/3 the power. NASA is interested in developing this technology because it's very convenient for sending large masses of material to Mars, for instance, or actually pretty much anywhere else in the solar system. So the armed spacecraft would demonstrate that technology, would also demonstrate gravity tractor deflection. So the asteroid is back here. This is actually the shape model of Itokawa. The rendering was made before they'd finalized EV5 as the target. They have a new version now, but I haven't updated my slides because the new pictures came out today. But anyway, the asteroid's back here. Its gravity is weak, but it's there. It's pulling the spacecraft down, and also pulling the mass of rocks that we've picked up down. We have our rocket exhaust. We angled the rocket exhaust so that it misses the asteroid. Momentum is leaving the system in the rocket exhaust. If we balance things correctly, that keeps the spacecraft in a stable position relative to the asteroid. Momentum is going this way, and the entire asteroid spacecraft system is getting pulled effectively up, or you can better to think of it sideways, because up and down are a little bit academic in this low gravity environment. But you very, very slowly pull this entire small mountain sideways just by standing the spacecraft next to it and having its gravity do the work. You don't normally think of pulling mountains towards you by standing next to them. But if you're in microgravity and you've got several months, you can pull EV5, which is 400 meters wide, several hundred meters off course. So the armed spacecraft would do that, and then it would fly the material back to the Earth for the astronauts to work with. And there's interest there in terms of space resource utilization. I mentioned EV5 as a carbonaceous chondrite. If it's like Orgwe, it's a few % water by mass. So there's a group here in Mountain View called Deep Space Industries. There's another company in Planetary Resources up in Seattle. And they'd be interested in sending up racks of equipment. The astronauts shove a bag full of EV5 bits into the test rig, and they demonstrate making resources in space. Now, this is not mining asteroids for platinum and selling that on the ground. That's more trouble than it is worth. But it's potentially making future space missions easier, because you can talk about making bulk mass products, radiation shielding, water for fuel, for life support. So that sort of technology people start talking about, really wanting to develop for human missions for deep space in particular, because humans require lots of infrastructure and consumables, and anything you don't have to carry up from the ground is great. But ARM by itself doesn't address that, but it gives you the resources to test out those technologies for space resource utilization at a meaningful scale in space. It also gives astronauts cool things to do to test out equipment for sending human missions beyond Earth, Moon, space. So the ARM mission developed as a compromise between NASA human spaceflight, NASA technology development, asteroid science, and impact hazard mitigation. And it addresses all of those goals pretty well, even if it isn't exactly what any one group would have come up with on their own. So NASA headquarters has endorsed this. Technology reviews are looking pretty good at this point after several years of work by very skilled engineers. My only input has been to say, this is what the asteroids look like.
Cool.
And they have to figure out the complicated problem of actually making all this work. Question now becomes, given final reviews are back on the engineering side, will Congress allocate the funding for this project? Now, this is coming out of NASA human spaceflight as opposed to NASA planetary science, which means there is a larger budget in absolute terms. But again, it requires Congress to allocate the funding to actually go ahead with the mission. So we'll see what happens. I encourage you to advocate for NASA funding, as always. Now, if the ARM mission does happen, but not on the same time scale, it gets pushed back some years in the future, there are other asteroids that we can go to, some of which we've already looked at with radar. One of them is Bennu. I mentioned it keeps having good opportunities for Earth flyby. It makes it Earth flybys. That makes it a good target. It's not quite as good as EV5 in terms of the amount of material you can bring back. EV5 itself, of course, comes back every 15 years. So you'd have to wait until 2040 after the mid-2020s timeline, which is a little bit long. So there's other asteroids we're looking at. So I've talked about quite a lot of stuff: asteroid science, asteroid impact hazard, asteroid space missions, and I'm just about out of time here, so I'll stop and take any questions you've got. So thank you.
Thank you. Fantastic. That was exciting. So, do we have any questions for our speaker? Lucas.
So I was looking at the radar images, and you said that someone was able to deduce that it was not a binary system, but in fact one solid near-Earth asteroid.
Yes.
Earlier in the slideshow. Could you talk a little bit more about how she was able to deduce that? Like, just looking at your images, like, see, you could, like, to me that clearly looked like, you know, two things orbiting each other, and I guess, was it just math that was saying that it was not two things orbiting each other rather than they were rather joined?
So there's a couple of things here. One is that if you know the orbital, if you know the orbital period of a separated binary, and you know the distance that they're separated, you can figure out the mass of the system. And if you've got two things that are separated by a few hundred meters and they're spinning every 10 hours, they can only be in orbit if their mass is really, really low. And so you end up with a situation where either they're two objects that are physically sitting on each other, or they are things with 90% porosity, which is probably unphysical, although we've seen some things with 50% porosity. The other thing, which really nails it for 2000 RS-11 in particular, and Toutatis and some others, we can actually see the joint in some of the pictures. So you see here in the upper images, it looks like there's two pieces that are separated because there's this gap here where things are entirely in shadow. But it rotates around, and you can see here the joint between the two components in the second row of images. And then that goes into shadow, and you've got the joint invisible again. And then half a rotation period later, which in this case is about 2 hours, you can see the other side of the joint. So there actually is you can directly visualize the contact all the way around the object. Now, getting the details and saying that it looks like this,
yeah,
that becomes a many-to-one inversion problem, and it takes quite a lot of work. There's a grad student right now at UCLA that I'm doing a little bit of work with. He's working with the General Radar Group, all of us who do this stuff. He's trying to improve the software that we use to reduce the data so we can handle this many-to-one inversion problem in a more computationally efficient way.
Cool.
Going back to that same slide we were looking at for this question, I understood the idea of figuring out the rotation based on the redshift of different parts, but I didn't really understand when you were talking about the different times, how you get another dimension out of that.
Okay, I'm actually going to do this without the screen share because it works better if I'm actually showing you some complicated shape.
Okay.
So try to turn the screen sharing off again. Okay. So we have object out in space. I time the time of flight of the radar signal. So we're coding the transmitted waveform in time. So I can tell you how much of the radar echo is coming from the side of the object nearest you, and then 100 meters further back, and 200 meters further back, and 300 meters further back. So you're getting slices along the line of sight. So that's the time of flight of the radar signal going out and coming back. And then the Doppler shift is giving you that second dimension, which is along the asteroid spin axis. Again, I can't immediately tell you if it's the object spinning like this, or if it's the mirror image of the object spinning the opposite direction. It's actually a common problem that will end up with this north-south ambiguity.
Right.
Because I can't tell which side of the equator I'm looking at something from.
So
again, if you get enough images from enough different angles, you can figure it out.
So you guys pulse the radar. And so
we don't pulse the radar.
Okay.
We code the transmitted waveform in time. It transmits continuously.
Ah.
We then do a convolution algorithm of the echo that we get back against the transmitted code.
Okay.
So there's a couple of different ways to do this. The one that's actually simpler to explain is we call it chirp waveform. We're changing the frequency of the signal rapidly in time.
Okay.
So we're transmitting one frequency now, a slightly different frequency a microsecond later.
Yeah.
And then any signal that, so that we're transmitting continuously, but we can reverse the echo pattern that we're getting, and at any given second, the echo coming back at a given frequency is coming back from a particular range position.
Does that make sense? Mm-hmm. Okay, so that helps a lot.
It gets a little bit more complicated because you're also getting frequency changes due to the rotation rate of the object. The deconvolution ends up being unique, but it's pretty processor intensive to do. But it's easier than making a system that can handle going from 0 transmitter power to a gigawatt of transmitter power to 0 transmitter power, and only transmitting 1 part in 1,000 of the time.
Right. Cool.
People have tried that sort of pulse radar technique, but it doesn't work particularly well because you end up with power surges everywhere inside your instrument.
Yeah. That's pretty cool.
In the back?
In the back.
So I was just wondering if you could kind of speak on how you got into researching asteroids for your general career track.
So how this worked was that I was doing physics and astronomy as undergrad in University of Minnesota. And I was liking radio astronomy and hardware, not so much the hardware, the software science. And then I was also interested in the planetary stuff, but there's not that much planetary science at the University of Minnesota. There's 2 or 3 people who do that. One of my advisors said, there's this guy named Steve Ostro at JPL who's doing radio astronomy of asteroids. You should talk to him. Steve offered me a job. It worked out.
So were you doing undergraduate research there at your institution, and that kind of put you in contact with people, and so you knew?
So I was doing undergrad research at the University of Minnesota, but it was not at all planetary astronomy or radar stuff.
Right.
Class projects, radio, optical astronomy, but the research I was doing was space physics.
Okay.
Understanding certain aspects of the aurora.
Oh.
Because the University of Minnesota has a very good group for space plasma physics.
Okay.
But they don't have so much planetary science.
Right.
Fortunately, Caltech was pleased to have me show up.
So in your experience, the students that go to Caltech or other folks who are active in planetary sciences, do they look for students that have had undergraduate research experiences or REU experiences that help them get better situated into that field?
Those do help, but it also helps, I think, for the students. Because it's been a while since I was a student.
Okay.
But I figure it's good, if you think of doing grad school, to go try the summer research program for 10 weeks. And if you find you do not want to do science research, then okay.
Right.
Or do something else. This is entirely normal.
Right.
Whereas if it's something that you do like doing, then okay, maybe several years of grad school is a worthwhile investment.
Are there any REU programs there at SETI, or
We do have an REU program. Our deadline was a month ago now, though, unfortunately. We're currently sending out offers. We had lots of good applicants, fortunately.
We will watch for it for next year.
Deadline is usually February 1 or thereabouts.
Okay.
Gene Char is in charge of administering the program here.
Cool. What sort of programming background or any other sort of ancillary skills might you recommend for young physics and astronomy undergrads?
So people come with a pretty wide range of skills. I do not have that much of a CS background. I can run stuff in C. I can run stuff in MATLAB and whatnot. But I still have yet to learn Python, which puts my skills about 15 years behind. I really should go do that, actually. But again, it depends on the projects you want to work on. If you want to be doing very detailed, low-level instrument, as I say low-level, very detailed instrument development,
right?
Well, that involves a lot more the hardware side of electrical engineering and mechanical engineering. If you want to be doing data analysis and whatnot, than what I do, then that gets into more mathematical methods of physics, model fitting, statistics, and so on.
Okay.
If you want to be doing planetary science, it helps to know some geology.
Mm-hmm.
So at Caltech, they actually have a program set up for this. So a lot of us came in planetary science having done astronomy mostly, and they had me take a bunch of geology courses in my first year of grad school. People who came in from really mostly geology background, they would take a bunch of astronomy courses their first year.
Cool.
Just to get everybody onto the same skill set. But that depends a lot on the particular program you're going into.
So was that Caltech program a really healthy environment? You really felt like that was a good place to hone your skills, and it was a supportive environment?
For me, yes, but not always. And it's a weakness of the current system that you end up often being at the mercy of luck in terms of who you end up having as your advisor.
Yeah.
I was lucky. Steve did a very good job.
Yeah.
Also, cancer sucks. He died some years back.
That would be awful, yeah.
Fortunately, he made the time to still work with me around chemo.
Oh, wow.
But there are a lot of advisors who are not supportive and exploit their students. You want to try to avoid those people. Good departments do not allow those people to have students, but it does sometimes happen because the culture is lacking right now.
Yeah.
And that includes Caltech. There have been a couple of cases I know of professors at Caltech doing very horrific things.
Yeah.
Fortunately, some of them have been fired, and this improves the culture of the department.
Yeah, definitely. That's where we had some sexual harassment issues pop up there, right?
There was a recent case, yes, in Caltech physics department, where there was a professor who has a very long history of being a creep.
Yeah.
He was allowed to get away with stuff for a very long time.
Yeah.
That should not have happened.
It's difficult when your undergrads are sort of like your children, and you want to send them to safe places so that they can learn and grow. And when you hear stories like that, you want to make sure that you send them to safe places so they can be better and not be in bad situations. So yeah, always have to research where you're going. Ask lots of questions. Lucas, you had a question?
Yeah, just a quick thing that sparked my interest. I don't know if you would know, but when you said that they were using xenon as fuel, I would have never thought to use a noble gas so much. Like they were just using it as sending it through the voltage gate and ionizing xenon gas. Wouldn't it be easier to ionize a different gas that wasn't like one of the noble gases? Or?
So you can use lots of different stuff for solar electric propulsion. Basically, all you need is so that you can ionize and run through a voltage drop. That returns to ionized plasma.
Right.
But the trick with using xenon is you have a trade-off between specific impulse, how much momentum change you get per unit mass of fuel, and thrust. So if you've got a very low mass thing like hydrogen, and you drop it through a given potential drop, it's going very, very, very fast by the time it comes up the end. So you get very high specific impulse, but you get very low thrust. If you have something like xenon, then you can get much higher thrust, but your specific impulse isn't as great.
Okay.
Xenon also has some useful properties because it's chemically inert, so it doesn't start reacting with the tanks. Now, it is a bit harder to ionize, so there's a slight power overhead there than some other things might be, but the advantages in terms of getting a good specific impulse thrust comparison and it being chemically very stable and fairly affordable tend to outweigh that. So it's one of the most commonly used one. There's been discussions of a whole wide range of other things. Iodine, bromine, although those are a little bit reactive. Argon, krypton, water, hydrogen, helium, lithium. Lithium is reactive. Several other things.
Yeah. That's interesting.
Makes sense.
Gallium and germanium aren't too bad because they melt at very low temperatures. And the advantage there is they are solid, so you don't actually have to have a pressure tank.
Right.
Same for iodine. You just have a brick, and you heat it up a little bit, and then you get the gas and run that through the pipeline.
Fire them off. Oh, that's a cool idea.
So that's sort of a design. Then you can in principle have a somewhat lighter tank because your tank doesn't have to withstand pressure to the same degree as a 400 atmosphere tank of xenon.
Right.
But at the same time, a little bit less massive particles coming out, your specific impulse goes up, but your thrust goes down. So there is this complicated trade analysis that the engineers have done, and I cannot speak to all the details.
Right. All right. One more.
My only other question was, how do you assign coordinate systems to those asteroids, especially when they have really complicated motions?
So the easiest thing is to define the coordinate system based on the object's spin axis. So if it's spinning in principal axis spin state, there is a pole direction. And this normal convention, we have an object at the North Pole, at the South Pole, it has east and west. Okay. Now, we also can define a 0 point in some scale. Typically, we use the long axis and say that's longitude 0. Although you can have arbitrary longitude sets as long as you remember what they are. And then you have in and out. Now, for some objects, that's not sufficient because they get concave. And then you actually have to use an entire triangular mesh or other polygonal mesh to describe the surface. So this one, it's described as a very large list of vertice locations and then all of the edges between them. And then when we're doing the shape modeling in the computer, we're adjusting those vertices around and seeing how that changes the fit to the images, which is computationally intensive, but gives you a pretty good answer. For optical images, you can just do the direct comparison if you've got two images from different angles, and you can do a 3D reconstruction. And again, the coordinate system typically ends up being something centered on the center of mass of the object, and then based around its spin axis. For Toutatis, which is in this non-principal axis state, things are a little bit more complicated. So we have a set of coordinates centered on the object. We have its principal axes and its center of mass, and then those move around the object's overall angular momentum.
Wow.
So it requires a fair bit of bookkeeping to keep all that straight.
So have you had mechanics yet? Classical mechanics, the class? Okay, you'll learn about his principal axes and what he's talking about more in depth in that class.
Now there is a trick that, of course, we work on the principal axis calculation. That's assuming the object has uniform density across its interior.
Yeah.
We just take the shape and compute the principal axis, moments of inertia. Right. So it may actually be slightly offset, the body center coordinates that we're using. They can't be too far off or our spin state model would be wrong. Yep. But there's some uncertainty there.
So that's very cool. That's very cool. Very cool. Do we have any other questions for our speaker? Well, let's give our speaker one more round of applause.
And thank you all again.
Well, Michael, thank you very much. This has been fantastic. I really appreciate your time. And we will be getting back with you. I'll send you an email later tonight or tomorrow with some follow-up for the seminar.
All right. Have a good night, everyone.
Thank you very much, man. Appreciate it.